All right, I'm assuming people online can hear me even though no one said anything. Welcome to 161 discussion 7. Discussion sheets are up in the front as always in case you need them. Today we're going to talk about SQL injection and cookies. So again, this is what was covered last week. And I think we're actually going to go into this in the reverse order. So maybe it should really be cookies and SQL injection. Not Discord. All right. So I know we technically talked about CSRF at the beginning of the week, which is not technically how we usually do things, but because it was covered early this week, I'm fine with it. So going into it really quickly, the issue with HTTP right now, or not right now, but that cookies is trying to solve is that it's inherently a stateless protocol. What this means is that if I send something to the web server, it sends me something back and then we're done. If I send another thing, there's nothing inherently that identifies me as that same connection. It's a completely new request. So the server needs some way of being able to associate two requests with the same session or the same user. This is stuff like shopping carts. If I go to Amazon and then later I go to Amazon again, I see it sends me back a page that has my items in it. So Amazon somehow has to know, oh, I'm the same user that requested a web page like 2 days ago or something. Same with same username, safe login sessions, and so on and so forth. We need some sort of stateful mechanism. The response to this is, or the solution to this is something called browser cookies. So the idea is that the server is going to send some information to the browser, and this browser is going to save that little piece of information. The next time the browser contacts the server, they're going to send that piece of information back to the server, and the server can look it up and go like, oh, I know who this is. This is the person that I sent that cookie to a while ago. So these are called cookies, and they're associated with domains and subdomains, and we'll get into exactly how that policy works in a bit. But I should share my screen. No, I am sharing my screen. So the general idea is we have this browser and we have the server. Let's say that this is the first request that the browser ever makes. So they're going to send just a standard GET request to this server. The server goes, oh, this is a new user. They don't have a cookie yet. I'm going to generate some random cookie, store it in some database, and then send the cookie to the browser. So you see it has this response here, and there's a header that says set the cookie to session equals, let's just say they generated B480 as their session. Let's say 2 days later, the browser comes back to the server, says, hey, like, I want to know what's in my shopping cart. They send this GET request again, and you see they attach this piece of information, ses equals B480. So now when the server receives this cookie, they can go, oh, I have a cookie. Let me look it up in the database and see, oh, it was associated with this user who had this shopping cart or something and so forth. So now they can send back a customized page that has like the user's username or the user's shopping cart or something like that. So these cookies add that stateful mechanism to HTTP that allows the server to recognize and distinguish different requests from the same user or the same session. Questions on how this works? Okay, great. Cookie policy is really just how we decide what cookies get sent where and who is allowed to set what cookies. So there's this domain attribute that can be set as part of a cookie, and this controls what cookies are visible for each domain. The rule that we say is that a domain is only allowed to set cookies for itself or any parent domain. So if I had a website like foo.161.org, it can set a cookie for its parent domain. So it can set a cookie for cs161.org, but not for anything else. So they couldn't do bar.foo.cs161.org, and they couldn't do bar.cs161.org. There has to be some, we call it a domain suffix of the current origin. It's the same thing for who receives cookies. So again, domain only receives cookies if it's set for its domain or for one of its parents. So same situation. Oh, I forgot to change that to foo.cs161.org. But the idea is it receives cookies from foo.cs161.org. and from cs161.org, but not say bar.cs161.org. We also have this idea of the cookie path attribute. So it's the same thing, except it's defined using the path of the request. So any page that's allowed to set a cookie can actually set any path. So even if I'm on like cs161.org slash, project 1, I can still set a cookie for project 2 or I don't know, Evanbot, or maybe even the root of the domain. However, a page only receives cookies that are set for its page or a parent page. So the example here again, if we have this request that's going specifically to /foo, then it's going to receive cookies that have a path set to root, which is the parent of everything, but not say path equals /bar, because that's not a parent of /foo. Pretty straightforward. Any questions on this? Okay, great. In terms of attacks, the main one is going to be the attacker can somehow guess or learn your, one of the main ones is going to be that the attacker can either guess or learn your cookie. Going back to the earlier example, I can pull it up here. No. Going back to this example, if the attacker somehow learns, oh, your cookie is B4AD, then they can just send their own request and say session equals B4AD. And the server will receive this, look it up and go, oh, that must be, Alice. I'm going to let them do whatever Alice is allowed to do. So if the attacker ever is able to learn or is ever able to guess the value of your cookie, then you've lost security. But it's even more subtle than that. Cookies are automatically attached to any requests that you make. So even if the user didn't intentionally click on a link that said, oh, I want to go to Amazon.com. If somehow your browser ever makes a request to that page, that cookie will get attached anyway. So the attack, I'll skip over this. Well, actually, no, I won't. What are some ways that the attacker could force the browser to make a request? Maybe not force, but let's say the attacker can somehow contact the victim. How could they get the victim to make a request to Amazon?
Having the victim click on the link.
Okay, sure. Let's say they click on a link. That is a pretty good way to get them to go to Amazon.com. What else could they do? Maybe the victim visits the attacker's web page. Is there a way to force the browser to make more requests?
Frames.
Yeah, frames. Frames are another good example. If you have a tag that says, oh, no markers. Great. Okay, I lost the front desk window. If you include an iframe that says, oh, you should also load Amazon.com/store, that will cause the browser to automatically make a request to Amazon.com. It's the same kind of thing with images, with scripts, and so on and so forth. So even if the victim knows, oh, never click on links to Amazon.com, if they visit someone else's website, that could also cause them to make a request, and that cookie will automatically be attached. So this is what we call a CSRF attack, a cross-site request forgery. I see you have a pen. Thank you so much. I'm actually just going to ask the front desk for it. But this is called a CSRF attack, and it's abusing someone else's already logged in session by making your own requests. So if you go to a website and that website causes the browser to make a request to like Amazon.com/delete account, that might be bad because your browser automatically attaches your session token and then your account gets deleted. It's a pretty simple attack conceptually. Are there any questions on this? Okay. In terms of defenses, there are a couple of things. If you set the secure attribute on your cookie, you will only send the cookie over HTTPS. So anyone who is listening on the network can't see your unencrypted HTTP requests, which contain your cookies. There's also HTTP only cookies. So this mitigates some attacks by not allowing JavaScript to access the cookies and thus like sending it to some other website. But note that if JavaScript just makes a request to somewhere else, that request will still contain that cookie. So it doesn't stop CSRF attacks, only directly leaking the value of cookies. There's the refer header, which is a typo from 30 years ago, which if the request contains the refer header, the server can check, oh, this request to delete the Amazon account is actually coming from attacker.com. Maybe I don't want to allow that. But this is generally not great because of privacy reasons. So generally, this isn't a great defense to rely on. And finally, the good defense to include is a CSRF token. So this is yet another token that you send to the victim, and the victim has to send it back in the request. Now, it can't be a cookie because we know that the browser will automatically attach cookies for every single request. So what we want is a cookie that is sent in a response, and it's only ever going to be sent back in a request that follows up to that response, not in like all requests ever, like in cookies. So this could be something like a hidden form field. It could be you set a cookie, but now the victim has to send that value in the cookie in some other part of the request. That's not the cookie. There are different ways you can implement this, but all of them rely on the same origin policy. They rely on not being able to access another origin's data. Questions on anything? Okay, in that case, let's go through the first question. Probably spend about 5 to 7 minutes. Feel free to ask questions at any point, except for right now, where I'm going to go run and get some markers from the center desk. The center front desk is closed. It's all the same to you. You'll actually have that marker.
my CSR again to rely on the correctness of state origin policy.
Right, let's say that a website sends a CSR token embedded in a form. So it's just contained in the response that is sent to the client. That has the origin of, say, cs161.org, right? So if a script running in attacker.com is able to access the contents of cs161.org, then they could just access that CSRF token from whatever's running in that origin and pull that out. So you need the same origin policy, which says, different origins can't access each other's data. Good question. Thumbs up if you're ready. Okay, it's like 2/3 of us, so why don't we take another 2 minutes and then we'll get started. Mark is dead. Do you have one? Thank you very much. All right. So first question, we basically get to talk about the same origin policy for a little bit. So we have our main origin, which is HTTPS and maps.google.com. And the question is, do these other requests have the same origin? So first one here, does this have the same origin? Thumbs up, thumbs down, thumbs up, same origin, thumbs down, not same origin. I see a thumbs down. Why?
Well, we have HTTP, but this one's HTTPS.
These are both HTTPS. I'm good. This is number one.
In the question is asked for HTTP google.com index HTML.
Oh, you're right. Sorry. Wait. Okay, wait. Wow, I read the top of the question and then it was completely different down there. Okay, thank you for catching that. Okay, we'll just go with that. Right. So the protocol here doesn't match. They're using HTTP and we have to match the protocol as well as the domain and the port in order to have the same origin. So this is not the same origin. What about number two, HTTP maps.google.com? Something thumbs up for yes, thumbs down for now. A couple of maybes. All right, so let's take this through one by one. This is HTTP. Is that the same as in the question?
Mm.
Okay. We have maps.google.com. Is that the same as in the question?
Mm.
Right, sorry, yeah, I keep confusing myself by looking at the top. Right. So because the domain doesn't match, that means it doesn't have the same origin. So this also does not match. All right, next one. How about HTTP google.com/home. All right, thumbs up for yes, thumbs down for now. A thumbs up and a thumbs down. Seems like the consensus is thumbs up, and in that case, you'd actually be correct. Looking at it again, we have protocol and HTTP, that's good. But the domain is google.com, that's also good. And both of these don't have port numbers, which implies that they are port 80. So there's an implicit port 80 here for both of them, that's good. So in this case, this actually is the same origin. And the thing to keep in mind here is that the path does not matter for the same origin policy. So that's something you can completely ignore. Only for the same origin policy, not the cookie policy. All right. Final one, we have HTTP maps.google.com. And we're at port 80. Look for yes. Move on for now. Right. I'm guessing what you're saying is this port does not match. What's it?
Domain also doesn't match.
Domain also doesn't match. Yes. So in this case, they both don't match. There's no like double negative going on here. It just doesn't match. All right. In terms of cookies, what we want is a cookie that's only sent to the map website and its subdomain. So what attributes would we have to set for this cookie?
The domain.
Yes, the domain. So that what would the domain be?
HTTPS and then maps.google.com.
So is HTTPS part of the domain?
No, that's not clear.
Right. So the domain would only be maps.google.com. And then in this case, it's a bit optional, but we know that the maps website will be hosted on HTTPS. So what might we want to do with this cookie additionally?
Set the secure flag.
Yeah, maybe let's make it secure. Just so that, you know, we're not leaking cookies all over the place. All right. Oh, never mind. That was part C. Forgot about that. Well, that answers part C. If you set the secure attribute, it won't be sent over an encrypted HTTP. Okay, so now part D, Google, which in case you haven't realized already, this is just Google, but with a B. Google wants to create custom websites for each user, and they can basically post anything they want. And they're suggesting, you know, each user gets their own subdomain. So maybe I get Nicholas.google.com. Maybe CS161 will get CS161.google.com. And so on and so forth. From a security standpoint, what might be the issue with this?
User websites could set cookies for Google.
Yes, exactly. So that's one thing. What I guess what would I have to set the cookie to be in order to set a cookie for Google.com? Domain equals what? Huh?
Google.
Yeah, don't overthink it. It's just Google.com. Nicholas.google.com is allowed to do this because remember, cookie policy says that a domain can set a cookie for itself and any parent domain. So google.com is a parent domain of nicholas.google.com, and thus they can set these cookies. It's also an issue because they can read any cookie set for google.com. So if you logged into Google and you were using like, Google Docs, um, nicholas.google.com could see those cookies and thus log in as you because they can see those cookies. So
So it could set and read cookies.
yeah, they can set and read cookies because you can always set and read cookies from yourself and parent domain. The technical term is domain setting.
Like, why is it called parent domains if it's like after?
Yeah, this was kind of like a debate that happened when people were creating the internet is should the parent domains go like to the right or to the left? They decided that the domains would go out to the left. That's why like .com is considered like a top level domain and that's why pretty much everything ends in .com, .org, so on and so forth. These are like the top level. And then next would be like google.com. And then we have like subdomains that keep going. So it's just kind of what we decided on. It could have gone the other way, but yeah, no good answer there, sorry. All right, so if this is a bad idea, what might be a better idea for Google to still host user content, but not interfere with google.com? This is a somewhat open question.
Still make it different domain. So instead of like username.google.com, it's like username dot like google.org or something.
Yeah, that would be a perfect suggestion. So maybe we'll have a domain that's specifically like Google user content dot doesn't really matter .com, sure. And now we would also have cs161.org or dot like I said earlier. But the idea is this domain and this domain are completely unrelated. They do share .com, but you can't do anything with that. So my content on here can't interfere or read anything from google.com. And if you look into it, that's actually what Google does. There's a Google user content.com domain that they put all the user uploaded content on so that it can't possibly interfere with stuff on google.com. Questions on this?
Why couldn't they just put Google and then .nicholas.com? Is that not like-
Because nicholas.com would be expensive. Because you have to, so each domain past like the top is its own like thing that you can buy and sell. So I actually own a domain that is ngai.me. ME is the top level domain, and I pay like $12 a year for ngai.me. And then I could do like google.ngai.me if I wanted to, because I control the subdomain since I control this parent domain.
Oh, so basically, I think of like top level is whoever's like owning it, and then underneath, like to the left is like all the sub stuff.
Yeah.
So in this case, Google is the one that's going to be hosting everything.
Yeah.
Okay.
Yeah. Exactly. Very good question. All right. In that case, let's move into SQL injection. So I have some very basic Go code here. I'm going to show my screen again. And the general idea with SQL injection that if I can move this over. The general idea with SQL injection is this %s right here. So there's a lot of extra stuff going on. All you really need to know is it's executing a SQL query that says select password from users where username equals quote %s end quote something. Now this seems pretty intuitive at first glance. If we did something like, oh, my username is Nicholas. What's going to get executed is Nicholas is the username, it gets substituted in here, and I get the password from users where the username is equal to the string Nicholas. This kind of makes sense, but we can start trying to break this. Now, if I sent I'm sorry, I'm not extremely bothered by the fact that that moves over ever so slightly. It's okay. And we set the username to be equal to a single quote. Let's see what happens. Again, just get substituted into right here. And we get username equals quote, quote. Okay, so that's the empty string. But then we have an extra quote here at the end. So this is actually a syntax error. I'm sure everyone in here is familiar with making syntax errors in any language. What happens is that the SQL server is going to say, this is not a valid query. You don't even have correct syntax. I'm just going to return an error. What's going to happen on the front is that the server, what you receive from the server is something went wrong. You know, there's been some internal server error. I can't continue. Now, this is a fairly innocent way of, you know, breaking this thing we have here, but we can be a lot more malicious with this. Let's say, oh, I want to not just select, you know, my password. I want to select pretty much every password in this database. I don't know why they would want to do that, but let's just say they want to do that. If we send quote or quote one equals one, or quote one, with that the end quote there. That looks weird by itself, but if we again take this and string substitute it into this %s here, let's see what we get. We want to select the password from users where the username equals, where the username equals the empty string. So that's probably not going to match any users because usernames are generally non-empties. Or the string one equals the string one. And we have this extra quote at the end because that was in this template. What's going to happen? How many passwords are going to be selected? All of them, yes, because we're saying basically or true, and anything or true is true. So we're actually just selecting everything from this database, and you can start to imagine why this might be an issue. This doesn't even have to be like select something. You could just do quote, semicolon, and then say like drop table users or delete from shopping cart. So you can be very malicious with this because this lets you execute any arbitrary SQL code that you want. That's basically my entire SQL injection explanation. Any questions on how this works or why this happens? All right, yeah, the general issue here is do not use string manipulation for manipulating other languages in general. The way to fix this is something called prepared or parameterized SQL. We're very inconsistent as to what we call it. The idea is instead of having this like %s string substitution and string manipulation, we actually just put a question. And what this tells SQL is parse this entire thing and just slot in the username at the very end. So what it will do is where username equals okay, just allocate like some space for it in the syntax tree. And then once it's done, it's like, oh, I need to know where username equals something. Then it's going to slot that username in. So SQL is what handles this, not a string parser. And that's going to mean that we can't do any sort of SQL injection attacks. Questions about how that works? All right, in that case, let's go into question 2, which I think is all the time that we're going to have for today. This one is, the first one is a fairly standard SQL injection attack. The second one goes into something called second order SQL injection, which if you're not able to get the idea right away, that's okay, because we'll talk about it at the end. Feel free to ask any questions that you may have. If not, we'll probably come back together in 10 minutes. Is everyone okay with me erasing this, by the way? My calculator is bad enough that I can't even check my email. Well, that wasn't exactly 10 minutes, but thumbs up if you're ready. Okay, we'll give it another minute. All right, so the premise of this question is that we are using a shopping site, and this shopping site blocks you from adding more than 72 of anything into the cart. So in this case, not more than 72 bags of pancake mix, which is probably a good thing now that I think about it. You can sort of think of it like there's an if statement up here that says if there's too many bags of shopping cart, or if there's too many of the item in the shopping cart, then they return error. So somehow, in executing this SQL statement once, we have to be able to insert 100 bags of pancake mix into the cart. Does anyone have any idea how we can do this? What do people put down as the answer? Yes, yeah. Well, there's nothing about this insert into statement that would let you add any ideas on now. Because basically what we want is like 100 rows in this items table. That's just like session token item. You have like A and then pancake mix, A, pancake mix. And we want this 100 pancakes, right? But if we just inserted, like if we just kept trying to do this over and over again, eventually we would hit this too many check and then it's. So how could we possibly maybe do all of this at once without having to go, well, how could we possibly add 100 bags of pancake mix all at once? Maybe as a hint, this value statement. If we have values 1, 2, 3, 4, this translates to a table that has 1, 2, 3, and 4. This is a 2-row table.
For item, you just kind of do that 100 times.
Do that 100 times. Okay, I think you're starting to go in the right track. So let's just say we leave the session token alone. So we'll just do values, and then let's say our session token is like ABC. And then what do we want to put in this percent s here? Let's say item. What is it called?
Pancake.
Okay, so pancake mix, let's just do PM. So, we're gonna get PM here.
Close the quote and
Quote,
parentheses,
comma,
and then session, like open parentheses, session token,
all right.
static. And so you get 100.
Yeah, so we're gonna keep doing this like 100 times. So, 100 times later, how do we need to make sure we end this? So let's say, we have another ABC. How are we gonna end this statement? Because we still have to handle what's at the end here. No, we probably want this pancake mix here still. What do we put after this?
Don't close parentheses.
Don't close the parentheses. All right, so no parentheses. Do we want a quote at the end?
No, no.
Exactly, right. Because what's going to happen is at the very end, they still have their quote and their parentheses here. So now, if we have this monstrous item and our standard session token, that gets substituted in, and you get values ABC pancake mix 100 times, and that all gets inserted at once. So this one's somewhat SQL syntax related, but it's a little bit outside of like the standard SQL injection attack that we showed you in lecture and discussion. Questions on this? All right, in the 1 minute that we have, what we're saying is that we have, excuse me. What we're saying is, okay, we have another piece of vulnerable code here, which I'm not going to write out right away. I can erase this by the way. So now they fixed this. This is no longer vulnerable. They're just using like question mark, question mark. Question mark, question mark. But they have this other query here. So what they do is they select the item from the cart, and then they execute another query, select item from cart, where session equals another %s. So the idea here is that they're executing they're executing a query from the database to get what the value of this item is. And then they're going to use that result from the query to execute another query. So if we fix this query up here, we know, okay, no matter what we try putting in here, this query is never going to be vulnerable. So whatever we put is always going to be put straight into this item basket. Does that mean that we can no longer exploit anything here? If just the endpoints are secure? If not, how could you possibly exploit this query? Where are we getting this item from? I guess according to the question. We executed. So this item, if we're looking at the code, we're getting like item equals db.query, and then we're executing some query, right?
So if like the first like query we just put in, like we just inject some code into it, and then the new queries that will be
Right, exactly. So what we're saying is, okay, I know I can't exploit this, but I know that whatever gets put into the database through here is eventually going to be used in this vulnerable part of the code. So I'll say, oh, item equals semicolon dash dash drop. And when we put that in there, it's fine because this is secure. But later, we're selecting this item and storing it in this item variable here in Go. And now we're using this in string substitution to exploit the SQL injection vulnerability. So it's not happening when we first make the request, but later when something is taken out of the database and then put into another query, that's when the exploit happens. Does that make sense? A couple of nods. All right. With that, that's all the time that we have. For context, this is called second order SQL injection because this would be the first order, this would be the second order. Just kind of something that we call it. But yeah, if there are no further questions, then I will let you go. Sorry for being 2 minutes over time. But thanks everyone for coming.